just to recap what we talked about last time, we touched on these concept of linear dependence of vectors. In 2 dimensions, vectors are linearly dependent if they are collinear or scalar multiples or parallel/antiparallel. All of these things mean the same thing for us in the context of 2-dimensional vectors. So if we've got 2 vectors that are, let's say, collinear or scalar multiples, we can write them as, we can write one of them, let's say we've got vector x, we can write it as a scalar multiple of vector v. Okay. If we can write this statement, we can find out what k is, so that this whole thing is true. That tells us that the 2 vectors are linearly dependent. Now, we can take this, and this is sometimes written as some scalar times x plus some other scalar times v equals 0. In other words, we can write these 2 vectors, if we add them together somehow and scale them up or down appropriately, we can get them so that they cancel out. Okay? And, of course, these scalars, a and b, cannot both be 0. Okay? I mean, if a and b were 0, then it would be trivial just to get the 2 vectors to cancel each other out. Okay? So, linearly dependent if, in 2D, if they're collinear, if they're scalar multiples, if they're parallel or antiparallel, these all sort of mean the same thing. In 3 dimensions, vectors are linearly dependent if they are coplanar. Okay? So if all 3 of the vectors lie in the same plane, we say that they are linearly dependent on one another. The other way of writing this was if, well, let's just say, if any one vector is a linear combination of the other 2. So if we can write one vector as a linear combination of 2 others, that means that those 3 vectors are, as we say, linearly dependent on one another. So this is sometimes written as, if we want a vector x, this is, and we want to write it as a linear combination of 2 other vectors, v and u. If we can find those 2 scalars, a and b, so that we can write x equals av plus bu, and then we can say that these 3 vectors, x, v, and u, are linearly dependent. Or we can say that they are coplanar. And of course, this is sometimes written as, just as we change this one up here, we could write this as, let's see, I've already used a and v here, so I'm running out of letters here to use. So we could use cx plus d v plus, we'll say, f u, although that's probably not a great choice of scalar and vector there. But if we can define 3 new scalars so that when we add these 3 vectors all together, they cancel out and give us 0, and then we can say that they're coplanar or that they are linearly dependent. So in this case, C, D, and F cannot be 0. Okay? Now, if vectors, and I'll just rearrange this a little bit here, if vectors are not linearly dependent, then we can say that they are linearly independent. I know this is blowing your mind here. If they're not dependent, they're independent. Okay? Now, the textbook has a little section where it talks about the significance of the fact that vectors are linearly independent. And it talks about using linearly independent vectors as a basis for a plane. or a basis for 3 space. Okay? I'm not going to talk about it here, but if you read that section of the textbook and you're a little bit confused, I've put an example and a little sort of mini lesson up on the D2L site that explains what they mean by a basis for a plane or a basis for 3 dimensions. Okay, so you could take a look at that. Okay. Now, I tried to come up with a question here that would actually make use of these properties that, that we've just talked about up above. Here's the best I could do here. If u, v, and w are linearly independent, and these 3 things are vectors, so I'm going to add my vector symbols here. If the vectors u, v, and w are linearly independent, find the values of r, s, and t if we've got this mess here. R times u plus 2s minus 1 times v plus r plus s plus t times vector w all adds up to 0. Okay. And the key to this question is that we're told that these 3 vectors are linearly independent. Okay. If they are linearly dependent, so let's just say, if they are dependent, we could write u, v, and w. Let's say we use our coefficients again, c, d, and f. Okay. If they were dependent, we could write this no problem. Okay? That's the definition of what it means for 3 vectors to be linearly dependent, just like we have up here. But we're told that these guys are linearly independent. So in theory, we shouldn't be able to write this because they are independent vectors. Independent vectors. Okay. They're linearly independent vectors. But we're told right here that we can do that. Now, the only way, if these are independent vectors, that we can get them to all add up together to 0 is if all of these coefficients, c, d, and f, are equal to 0. So the fact that these are independent vectors and they sum to 0 tells us that all of the coefficients, those scalars on each of our 3 vectors, must be 0. So what does it mean for this statement that we have up here? Well, let's take a look at our scalars here. Our first scalar here is r, so r has to equal 0. Our next coefficient here is 2s minus 1. That has to equal 0. Our third scalar here is r plus s plus t. That has to equal 0. Well, we've already found out, what we're trying to find out is what are r, s, and t. We found out what r is. R is 0. We can figure out what s is just by solving this equation. 2s equals 1. So s has to equal 1/2. And once we know r and s, we can figure out t over here. We know r is 0, s is 1/2. If I add them all up, they have to equal 0. So t must equal 1/2. And all of this flows from the fact that these are linearly independent vectors, but we could add them all up together to create 0. Okay. Now I'm going to